This lecture is going to talk about the first law of thermodynamics. Now, the first law of thermodynamics is conservation of energy. We're going to be looking at conservation of energy in the context of a closed system to begin with here. So conservation of energy is a balance between energy crossing the system boundary and the change in the system's energy. Now, because we've already done quite a bit of work on defining different terms, most of the things we need to talk about in connection with conservation of energy, we've already done so. So there's three important quantities that we've talked about earlier in the course that I want to review. The first one is heat transfer. Remember that heat transfer is energy crossing a system boundary due to a temperature change. The second thing I want to review is work transfer. And work transfer, again, is energy crossing the system boundary, but due to anything other than a temperature change. So notice that Q and W, heat transfer and work transfer, are the only ways that energy can cross a system boundary. So in terms of balancing energy crossing the system boundary, Q and W are the only things that we need to include in that, because they include everything. The third thing that we talked about earlier was the idea of total energy, and capital E was the symbol that we used for that. So the total energy is the total energy associated with the system. So that's internal energy, kinetic, and potential energy. So these three things are the only thing we need in order to write down a conservation of energy equation. So this illustrates our system. So this shape here is our closed system. So remember, no mass flow across that system boundary. We've shown the heat transfer here and the work transfer here. And the direction of these energy transfers I've shown as positive. Remember, we talked about the sign convention for these two quantities. Heat added to the system is positive, and work done by the system on its surroundings is positive. So those are the two energy exchanges with the surroundings, and when those happen, they result in some change in energy of the system. So the first law of thermodynamics can be written like this: Q minus W equals delta E. All of the things crossing the boundary and the result of those things on the system. Now notice this negative is here because of our sign convention for work. Work done by the system on the surroundings is considered positive, but that of course serves to reduce the amount of energy in the system. So that explains why there's a negative sign there. Now we want to expand this change in the system energy and just remind ourselves what it is. So it's made up of internal energy, kinetic energy, and potential energy, as we talked about in the introduction. For all of the systems that we're going to look at in this course, the kinetic and potential energy changes are going to be zero. This is certainly true for the closed systems we're going to look at. When we look at open systems a little bit later on, kinetic energy changes will certainly be important in some of those. So for the purposes of this course, the right-hand side of the first law will usually be written as a change in internal energy. But we should remember that these two things are also part of the total energy. So when we use this equation, we will be including in our assumption list that we're neglecting kinetic and potential energy changes. Now let's review a couple of important characteristics of these three quantities. Here we show a process on a PV diagram. So we're going from state 1 to state 2. But of course, there are many different paths that we can follow in getting from state 1 to state 2. Now it's important to remember that heat transfer and work are both path functions. That means the amount of heat transfer as we go from 1 to 2, or the amount of work transfer as we go from 1 to 2, depend on the path we follow. Now in the case of work, that's a little more clear to see because we've learned that work is the area underneath the curve on the PV diagram. So clearly the shape of this curve is going to affect the area underneath it. So both of those are path functions. However, the right-hand side energy is a property of state. That's a state function. So that is not path dependent. It only depends on where these two endpoints are, not how we got from one to another. So the two quantities on the left-hand side of this equation are path functions. However, the difference between them is not. It's a state function. And we can make use of that fact when we're solving problems. Now I want to just review different forms of the first law. So we may see the first law written in different ways, and I want to understand exactly what the differences are. So this is what we've seen so far. Q minus W equals delta U. Now notice these are all uppercase letters. So in the notation we're using in this class, those are total heat transfer, total work transfer, total change in internal energy. And when I say total, I mean they are not on a per unit mass basis. So if we were using SI units, the units of these would be kilojoules or perhaps joules. Very often we will see the same equation but written on a per unit mass basis, and the only difference in notation is these are now all lowercase letters. But of course it's important to realize that if one of these is a lowercase letter, they all have to be lowercase. So you either need to do all three terms on a total basis or all three terms on a per unit mass basis. We also have a molar version of this, where the amount of substance is a kilomole instead of a kilogram. And in this class, remember, we denote molar quantities with a bar over top of the quantity. And again, if there's a bar over one of these, there has to be a bar over all three. Another form we'll see this equation in occasionally is a differential form. So this is just a very small change in the internal energy. So we're moving along a path, a very small amount. The internal energy changes by an amount du. And on the left-hand side, we have a small amount of heat transfer that occurs during that small segment of the path, and a small amount of work transfer. Notice we use a little bit different notation on the right-hand side and left-hand side of this equation. When we're talking about something that is a function of state, like internal energy, we use a d to represent a differential amount of that. And that's, of course, how we're used to doing this in differential calculus, dx, dy, and variables like that. However, in thermodynamics, we like to remind ourselves that these things are path functions and not state functions by using a different symbol to indicate a small amount. And we use a delta for that purpose. So delta Q, delta W are small amounts of heat transfer and small amounts of work transfer, but the delta is used as a reminder that these are path functions. The last form is one that we won't use very much, if at all, in closed systems, but we'll see something similar to this a lot in open systems. So this is rate form. So the dot on top of each of these quantities is a rate. So that's a time derivative, essentially. So this is now a rate of heat transfer. So whereas this would be kilojoules, this would be kilowatts. Likewise, a work transfer, a rate of work transfer, and a rate of change of internal energy. The next thing I'm going to review is how to calculate delta U. So we're focusing for a few minutes here on the right-hand side of this equation. Well, evaluating delta U, we need to pay attention to what type of substance we have. So if we're talking about water or one of the refrigerants, then we need to use the tables in the back of our textbook, as you've learned to use in tutorial 1. So those are all contained in Appendix A. So we have to resort to tabular information to get the internal energy for those types of substances. And remember, the thing that's unique about those substances is that their critical point is such that we are typically operating in or near that liquid vapor region. So the relationship among the properties is quite complex, and we use tabular data to take care of that complexity. If, on the other hand, we're dealing with ideal gases, then we're far enough away from that liquid vapor region that there are some simpler models to get the internal energy. We can get the internal energy from the integral of CV dt. And the most straightforward way to solve that for hand calculations is to use tables that have already done it for us. So typically we'll be using tables to calculate the change in internal energy for ideal gases. Now these tables, these ideal gas tables, are much more straightforward than tables for a substance which is changing phase. And we'll be looking at table A22 for air and A23 for other gases. The last option here is ideal gases still, but when we're willing to assume constant specific heats. So if the temperature change is limited, then we can assume constant specific heats, and we can calculate delta U from CV delta T. So in that case, there's a direct connection between the temperature change and the change in the internal energy of the substance. The next thing we'll look at is a couple of special cases, or a couple of special processes that simplify the first law in a certain way. First one we'll look at is a constant volume process. So V is not changing. So this would be a vertical line on a PV diagram. So we start with our full form of the first law for a closed system, Q minus W equals delta U. But we remind ourselves that since it's a constant volume process, the work is zero. So with the work being zero, that tells us right away there's a direct connection between the heat transfer and the change in internal energy. We've just eliminated the work. So Q equals delta U for a constant volume process. Now realize that this equation is valid regardless of what substance we're talking about, because we haven't made any assumptions here about what the substance is. We've only said that the work is zero for a constant volume process. However, moving on from this, if we say we're dealing with an ideal gas with constant specific heats, as I said here, then Q is CV delta T. So the heat transfer equals the specific heat times the change in temperature if we have a constant volume process. The other process we're going to look at is a constant pressure process. So on a PV diagram, this is a horizontal line. This simplification doesn't come quite so quickly because we can't just cross off one of the three terms in the first law in this case. They're all changing. So we'll see how this works out. Notice that I'm starting here with the differential form of the first law, but this is still really Q minus W equals delta U, just for a very small process, or a very small segment of a process. Now let's take a look at the work in this equation. Well, work is equal to P dV. So delta W is equal to P dV. Remember, work equals integral P dV. So delta W, put a delta here, get rid of the integral sign. Delta W is equal to P dV. So that's the connection between work, pressure, and the change in volume. Now let's take a look at the product of P and V. So we want to focus on the product of P and V. If we take the derivative of this product, and we can use the product rule, and that is P dV plus V dP. So notice these are the same thing. So that means we can write delta W like this. Delta W is P dV minus V dP, just moving this over to the other side. Okay, so what we're going to do next is take this and put it in there. So our first law becomes delta Q minus dPV plus V dP equals du. So we've just replaced the work with these two terms. Now here's where we remind ourselves that we're looking at a constant pressure process. So this term is zero because dP is zero for a constant pressure process. So we can eliminate that term for a constant pressure process. So this is what we have so far. We've just moved this dPV over to the right hand side. Now we can combine these two things together And it'll look like this, because if we were to differentiate this, we would get that. It's just a sum here. So we see on the right hand side here, we have this combination of thermodynamic properties. Remember, all of these are state functions: internal energy, pressure, and specific volume. Well, this particular combination of thermodynamic properties has another name, and we've seen that up to this point. We just haven't defined it like this. That combination of properties is enthalpy. So H is equal to U plus PV. We're going to talk a lot more when we get to open systems about the physical significance of these two terms, but right now we're just going to define H as U plus PV. Well, that means that for a constant pressure process, delta Q equals dH. Now this equation is still in differential form because I've been working with differentials in order to get there. However, if we look at an entire process, this will become Q equals delta H. So the total heat transfer that happens during the process is the change in enthalpy. So up to this, we haven't made any assumption about what type of material this is or what type of substance it is. So this is valid for any substance. Any substance at all undergoing a constant pressure process, Q equals delta H. However, if we're talking about an ideal gas with constant specific heats, then delta H is equal to Cp delta T, and we can say Q is Cp delta T. So I want to summarize the results of these last few slides where we've looked at a constant volume and a constant pressure process. So remember, here we're talking about an ideal gas with constant specific heat, Cv and Cp. If we are calculating Q, then we need to make sure that we respect this requirement that it be a constant volume process for this equation to apply, and a constant pressure process for this equation to apply. So Q equals Cv delta T only for a constant volume process. Q equals Cp delta T only for a constant pressure process, because we made those assumptions in order to get to those equations. Those are the two equations we developed in the previous few slides. Now, if we're calculating delta U or delta H using Cv delta T or Cp delta T, we can apply that to any process. So these are only valid for constant volume and constant pressure, whereas these are valid for any process as long as it's an ideal gas with constant specific heats. So that's a very important thing to remember, so that we don't, first of all, violate these assumptions by using these equations when this is not true. But just as important, we need to realize that no matter what the process looks like, we can still use these ones. So if we need to get delta U and delta H for any shaped process, these are still okay. It's only if we want to calculate Q directly that we have to pay attention to these conditions on those two equations.